we want to check the relationship between the logarithmic function and the gamma function. So we are going to be proving these three things very quickly. The first one, I have an integral from x to x plus 1 of gamma of z, the differential of gamma of z, then this z. So now, in this case, look at what we are going to be doing here. Well, this is what we are going to be doing here. You know from law of logarithm, from standard integrals, that whenever you have what you have at the denominator, if it is the differential that is in the numerator, the answer is log of the denominator. That is, if what you have at the denominator, if you differentiate it and that's what you have at the numerator, the answer is log of the denominator or ln of the denominator. So in this case, this one will just be, obviously, this one will just be log of gamma of z. Then put the bound x plus 1. So this one will become log of gamma of x plus 1 minus log of gamma of x. Don't forget, we know that gamma of x plus 1 is s gamma of x minus log of gamma of x. So this one will become x root x. You know, this is product. So from law of logarithm, I can write this as log s plus log gamma of x minus log gamma of x. Log gamma of x minus log gamma of x will give me 0. It will be out. It will cancel out, so I'll be left with log s. And I'm done with the first one. Log s is equal to this. I'm done. So the second one will be, I have similarly the same thing, just the way we applied the first one. That's how we are going to be applying the second one now. Similarly, since what is at the denominator is the integral of what is at the numerator, this one will become log of gamma of z. Then I have from 1 to n plus 1, right? So this one will become log of gamma of n plus 1 minus log of gamma of 1. Of course, gamma of 1 is 1, so but log 1 is 0. Log 1 is 0. So, and this one, gamma of n plus 1 is n factorial. So minus 0, which is equal to this. So the answer is log of n factorial, as you can see in the second question. Now the third one, we want to prove this third one, that gamma double the second derivative of gamma all over gamma is equal to all these things I've written here. Look at where I'm going to start from. I'm going to try to differentiate gamma of z, differential of gamma of z all over this. I'm going to differentiate this. This one is to differentiate. Let us differentiate this using quotient rule. You know, I will first have gamma of z first, then differentiate what is on top. Don't forget, what I have on top has been differentiated once. So if I'm differentiating again, that means I'm differentiating it twice. Double derivative minus, then what is on top, that is gamma of z. Then differentiate the denominator, that is another gamma of z, all over the denominator square. That is what I have. So this one will become equal to, now I will separate it so that this one will become gamma of z, gamma second derivative, then I have gamma of z all square plus, then this one gamma of the derivative of z, like derivative of gamma and derivative of gamma, I have two of them to become square, so that I have gamma of z all square over gamma of z all square. So this one will become this one over gamma of z, right, is equal to gamma of z cancel gamma of z, so that you will be left with second derivative of z over gamma of z. One of them will cancel out, plus square is common here, so I can just have gamma of z over, so I've changed the minus to plus, this is minus gamma of z all square. So take this to the other side, so that you'll be left with this one here, so that at the end of the day you'll be having second derivative of gamma of z over gamma of z will be equal to this gamma of z over gamma of z plus gamma of z all square. And that is the proof of what I have written there. That is the answer. Hello everyone, so you are welcome to this video on the beta and gamma function. So in this video I'm going to be giving you tools of like all the tools needed for evaluating the gamma function. All the tools needed, like all tools needed that will help you evaluate the gamma function. That's number one. So if I'm going to be giving you all the proofs, all the tools without proving it. I have proved it. Most of the tools have been proved in my previous video, in my previous lecture, and the one I have not proved in my previous lecture, with the knowledge of the one you have you know already, use it to prove it yourself. And I'm telling you, it's going to be quite simple if you have followed on my series on beta and gamma function till this stage. Thank you. So the first one, gamma of z plus 1 equals z, gamma of z. That is the first tool. Another one, so that means if you want to evaluate maybe gamma of 7 over 4, gamma of 11, this tool is very important. The second one you need to know is gamma of negative. If you have negative 1 minus z is equal to minus z, gamma of minus z. This is also another useful tool you might be needing depending on the question you want to solve, but this is majorly for negative arguments, that is gamma of a negative value, gamma of a negative real numbers. This is very important. Now again, the third one, of course, gamma of 1 is same thing as gamma of 2, and the answer is 1. This is basic. We have done that before. Number 4, gamma of n plus 1 is equal to n factorial. We know that especially when n is an integer, so it's a positive integer. So you have this. Number 5, gamma of z plus n all over gamma of z is equal to z plus 1, z plus 2 till you get to z plus n minus 1. You can prove this one. This is also quite simple. You can prove this one. You can even use this property to prove this. It's quite simple. Number 6, the next one, gamma of z over gamma of z minus n is equal to z minus 1, z minus 2 till you get to z minus n. So z minus 1, z minus 2 till you get to z minus n. So when you have this one is also gamma of, this is also what you have here. It's also another useful tools you need to put in place. Number 7, the next one, when you have gamma of minus z over gamma of minus z minus n, this is equal to minus 1 raised to power n, gamma of 1 plus z plus n all over gamma of 1 plus z. So that is what you are going to have as well. This is what we are going to have in this case. Then number 8, limit as n goes to infinity of gamma of z plus n all over gamma of n raised to power z is equal to 1. So in this case, this is also another property of the gamma function you need to know. It's also part of the tool The next one, number 9. Number 9, gamma of 1n plus 1 over 2 is equal to root pi all over 2 raised to power n 2n minus 1 double factorial. So 2n minus 1 double factorial. Double factorial means when you have double factorial this way, it means you are going to be skipping double step. This is equal to n minus 2, n minus 4, like that, till you get to 1 or 2, whichever one you get to first. So this is double factorial. This is the definition of what you call double factorial. This is also important. This is also part of the tools needed. The next one, number 10, gamma of 1 over 2 minus n is equal to minus 1 over raised to power n 2 raised to power n root pi all over 2n minus 1 double factorial. Of course, we've defined what we call double factorial before now, and this is what we have. So this is the answer. So this is what we have. So now the next one, number 11, gamma of n plus 1 over 3 is equal to 2 multiplied by 5 multiplied by 8 and on like that. You get to 3n minus 1 over 3 raised to the power of n gamma of 1 over 3. This is also another important tools that can be useful in gamma function. Depending on what you are looking for, depending on what you want to find, you can just choose it directly and you'll get your answer. Number 12, gamma of n plus 2 over 3. Gamma of n plus 2 over 3 is also 2 multiplied by 5 multiplied by gamma of n plus 1 over 3 is, this one is gamma of 2 over 3, gamma of n plus 2 over 3. So please take note of that. This one is gamma of n plus 2 over 3, and this one will also be 2 over 3. Now, let me now write for 1 over 3. Gamma of n plus 1 over 3. This one will give me actually 1 multiplied by 4 multiplied by 7, and it goes on to 3n minus 2 till you get to all over 3 raised to the power of n, then gamma of 1 over 3. That's what we have. Then number 13. Gamma of n plus 1 over 4. What will this one become? For this next one, gamma of n plus 1 over 4 will be 1 multiplied by 5 multiplied by 9, and it goes on till you get to 4n minus 3 all over 4 raised to the power n gamma of 1 over 4. Number 14, gamma of n plus 3 over 4. Gamma of n plus 3 over 4 will be 3 multiplied by 11 multiplied by 3 multiplied by 7 multiplied by 11. You get to 4n minus 1 all over 4 raised to the power of n gamma of 3 over 4. So please take note of all these things in case you have a question to solve and you need some of these tools. You don't need to start proving from the scratch. You don't need to start from the scratch. You can just make use of all these tools and you will get your answer with immediate effect. Now the next one, number 15, gamma of z, gamma of minus z is equal to minus pi over sine over z sine pi z. This is also another property of the gamma function that is also very, very useful. Number 16. Number 16 is gamma of 1 over 2 plus z, gamma of 1 over 2 minus z is equal to pi over cos pi z. So some of all these things I told you before, we have proved them in the previous lecture on beta and gamma function. Why some have not been proved. You can do well to prove the one that I have not yet to prove, and it will be quite straightforward with all what you've learned in gamma and beta function so far. So this is also this. Now number 17, the next one, all the tools needed. That's what I talk about. So I'm going to be writing all the tools needed or all the useful tools in gamma function. Number 17, gamma of 2z. Gamma of 2z is 2 raised to the power of 2z minus 1 all over root pi. Gamma of z. Gamma of z plus 1 over 2. Number 18, now gamma of 3z is equal to 3 raised to the power of 3z minus half all over 2 pi gamma of z. Gamma of z plus 1 over 3 gamma of z plus 2 over 3. So that is what we have in that case. Then let us now write the value of gamma of 1 over 3. Gamma of 1 over 3 is actually equal to 2.678938, and it goes on like that. Number 20, gamma of 2 over 3 is actually also equal to 1.354118, and it goes on like that. 21, gamma of 1 over 4, 3.625600, and it goes on like that as well. Number 22, gamma of 3 over 4 is equal to 1.225417. So that is what we have. So these are all the tools I have on the beta and the gamma function. Thank you very much. So in this video we are going to be talking about other functions briefly, just brief summary of other functions. And why am I talking about these two brief on this brief function, that is the factorial function, and the second one I'm going to talk about is the Gauss PI function, because there is a relationship between the factorial function and the gamma function, as well as the Gauss PI function and the gamma function. That is why I'm talking about them briefly. So again, let A be an element of R, let A be in R the set of real numbers, then the factorial function of A over n times, that is how we call it, factorial function of A over n times, which is denoted as, this is how we denote it, factorial function of A over n times, we given as A plus 1, A plus 2, A plus 3, you get to A plus, what is at the subscript, A plus n minus 1. Before you get there, that's where you stop for all n greater than or equal to 1. Now, for real values A of 0 is equal to 1. A of 0 is equal to 1, and for A different from 0. Now, by this definition, we have what will be 1 factorial function of 1 subscript n. This one will be, from this definition, this one will become 1 multiplied by 2 multiplied by 3 multiplied by 4 till you get to 1, that is A. A here is 1 plus n minus 1. 1 plus n minus 1 will give me n. So that means 1 times 2 times 3 times 4 till you get to n. The answer is n factorial. So that means that 1n is equal to n factorial. Don't forget, n factorial is gamma of what? N plus 1. So now, from gamma function, we know that gamma of A plus n is equal to what? By the first, on the summary list of what I gave you the other time, recall that gamma of z plus 1 is equal to z gamma of z. We know that already from the elementary of gamma function. So gamma of A plus n, this one will give me A plus n minus 1 gamma of A plus n minus 1. And if you continue the process like that, you have A plus n minus 1. This one will become A plus n minus 2, A plus n minus 3. The time will come, you will have to get to A gamma of A. Actually, when you exhaust all the n here, if you write 10 times, you exhaust all the n, so that you come to a gamma of a. So that means that if you look at this very well, gamma of a plus n is equal to, this is a plus 1, a plus 2 till you get to a plus n minus 1. A plus 1, a plus 2 till you get to a plus n minus 1, which is factorial function of a subscript n. So that means this is a subscript n gamma of a. So we can make gamma of a the subject of formula. So gamma of a will be equal to this over a n. This is also this part of the relationship between gamma function and factorial function. So that is on that one. Let me just quickly talk about the second one, Gauss PI function. The second one, this is the first one. The second one, Gauss PI function. And what is that one talking about? It is denoted by almost like a product n, and is defined by, because pi function of n is equal to gamma function of n plus 1. So they are actually the same, because pi function of n is equal to the gamma function of n plus 1. So that is what we have, where n is a positive integer. Where n is a positive integer. So that is what we have. So, and also where, this is what we define it to be rather. So when n is a positive integer, comma, then the Gauss PI function of n will be exactly n factorial. Thank you very much. This is the end of the series of the open shape of the beta and gamma function. You need to wait for the new rep. The new rep, you are going to be seeing different definition of the gamma function. Weierstrass definition. All what we have been talking about here is just on the integral definition of the gamma function. We have just been using integral definition. We have to look at the Weierstrass definition, the Gaussian definition, and some of all these definitions we have. We have more than one definition, and you will get to know that the gamma function is an extension of the factorial function to the real line. Please kindly subscribe to my YouTube channel. Thank you very much. If you still to do that, and just leave my left